Right, let's take a look at this part. Is graph bipartite. So there's an undirected graph with n nodes where each node is numbered between 0 and n minus 1. Okay, you're given 2D array graph where graph U is area of nodes that U is adjacent to. Okay, graph U, alright. More formally, for each V in graph U, there's an undirected tag between node U and V. Okay, there's no self edges, alright. Right. So there are no parallel edges. Duplicate values. Duplicate values. Okay. If V is in graph U, then U is in graph V. This is okay. Graph is undirected. Alright, so I just have to take a look at the upper left, upper triangle. So the graph may be connected means there may be two nodes UV such that there is no path between them. Graph is bipartite if nodes can be partitioned into two independent sets A and B such that every edge in the graph connects to a node in set A and a node in set B. Right. So we just want 2, right? So this is false. This is true. And why is that? Alright, so from this side, you can just I think it's related to a two coloring problem, graph coloring problem. So can you color this in a way that this is like blue, this is red, right? And then the reds are not connected to each other, but here, as you see, they're connected. And how do we make sure that that's the case? From 0, we just make the other half. We create 2 lists. From 0, we maybe like this. So we put 0 here. We put 1, 2, and 3 there. Okay, just give me a second. Alright, so if I have this, and then later on, from the second one, from the connected ones, okay, if I think about this one, when I go to that, from this, I check the neighbors. If they are different neighbors, this is in the other side, it's fine. If you put this the other side, yeah, that's fine. So we just go on like this. I guess that will be it. I guess that can work like that. So I have 2 dictionaries. But what if I start with one of them? I think that's possible. It's possible. Partition 1. Partition 2. For every element in this graph. Wait, this is a JSON list, right? Alright, that's good. That's good. That's not 2D matrix. It says 2D array graph. Alright, nice. Okay, so for every one of them, maybe I should have this as let's see if I have a recursive way of this. I think that's possible. So if I have helper function, so partition 1, partition 2, current, I feel like I should have 2 colors for this. So if I also need to pass the graph, everything passes, return true, return false if in some case here. So I get the first one. Just call this helper graph partition 1, partition 2. The current is the first element there. Also, maybe you have visited no current. Fine. And here. So if the graph I, okay, just 1 second. So here, if graph I j is not in visited, then I call this. And I need visited here, set that. Right, and then here we call visited add current. Yeah, 1 0 to n, right? And -1. Alright, let's go. So at this position, this is visited for that particular thing. Should I have more than that? I'm not sure. Let's see, put this here. So okay, I guess I need these. So what happens here is that for for every graph I need to pass my current ID. For every current, for every neighbor in graph current, if so for every one of them, I mark them. Let's see. If 1 0 to 0 to 1, we go to 0 and 0 for every neighbor. We put those in opposite. So if partition 2. So the first thing that I want to check is that I start with one of them. This 0. I go n, current is 0. Now I add 0 to visit it. And here partition current is equal to partition 1 current is equal to true. Okay. And then for every neighbor partition neighbor if neighbor is in partition 1, return false. Okay, I guess I might have cannot do this. Maybe it says something close. See, okay, looks like it has some colors. We color it. Python. So for every position, I in color. Let's give it an idea and then try to change it. So we have some sort of, instead of visited, I will have this color, just color them. This color for graph current thing. If I in color else. Yeah, I guess I should spend some time and understand this first and then explain it here. Right, so I checked it, and there are a few solutions. And using breadth first search and depth first search, I tried to implement a recursive depth first search, but I couldn't finish the implementation. I'll be doing iterative depth first search, and for that, like I tried, I will need a color dictionary. I'll return true at the end. Here I will have for loop for every I in range of so for every node I'll do the first search. So I basically create a stack and color I equal to 0, and while stack I have to pop stack that append I. So while I'm stack, so we'll pop from stack, and then what I want to do here is that for every neighbor in graph I want to check if the first thing I want to do is that check if it has a color. Oh, by the way, so when I pop it here, the first thing I want to do is that if temp is in color, if it is not in the color, I want to continue. If it is in the color, I want to continue. If it is not in the color, I want to mark it as color temp 0 or something like that maybe. And then if color neighbor is equal to color current temp, I want to return false, else color okay actually, so the first thing that I want to do is that I want to check if name in color, not in color, color neighbor should be equal to color temp and my x over 1. I want to just change it, and later on, okay, this should be this base case. Just 1 second. Right, so here, not in color. Okay, I have to add that to not in color. I want to append it to the stack, the neighbor. And here I should take this to this. Maybe put this in here because I don't want to put it there. Why is not in color? If it's colored, we don't want to continue. If it is not colored, I want to create a stack for that, and then color I, color 0. Come here, I pop it. Marked as 0. Actually, do I want to do that? A puppet is already 0, right? The ones that are in this, they're all already 0. So I have I have this temp. I come here, I check neighbors. If they're not colored, I color them. And I add them to the stack. And if they're colored, I check if they're equal to the color temp. In that case, it is false. Otherwise, I just return true. I think so. It should work. Alright, so let's submit it. Okay, I have some cases here. There's that passing. So for I, nothing color. Check. Black stack, continue. Okay, I'm gonna check one thing. Right, it looks like here, this should be temp. And when I do that, it passes all the cases. So I forgot that I should be looking for the child nodes of temp. I was looking for the first node taken from the graph, but here I should just take it from the stack. So this is basic iterative DFS, but with some different conditions here. Normally it is just this, but instead of that, I also check for the color check and if it is in the color or not. So yeah, that was it. It's a pretty different problem. What's the space complexity times space complexity? It is okay. So the time complexity is of n times the number of edges. For every edge we go in. The space is of okay. When we mark it, we don't go in again, so we sum it here. The space complexity is the we mark color everything, so it is often like that. Okay, I think that's. I'm actually gonna check it from the solution. Right, actually it is true, so which is good. Right, so yeah, that was it. So we basically go over every node, and in every one of them we check if they're colored. If they're colored, it means that there is no problem. But if they're not colored, we want to check if there is a problem in the child, in their children. So we color it as 0, and we add them to the stack, and then do that for search with using iterative way. And here I just pop from it, and then in this for loop we go over its neighbors, and I have two simple checks. One is if it is colored. If it is colored, it means that we colored it previously before, and then it should match the, it shouldn't match the temp node's color with the neighbor, because otherwise we don't have valid partition. There's a problem. It's not possible to have wide partition. So in the other cases where we don't have them as colored, we just basically change the color of the, like put the opposite color to that neighbor. All right, so that's it.